Good morning and warm welcome to all the participants of this program. And today we have with us uh, Dr. S. Ramaya Pillai. Ma'am is scientist fish processing, ICAR-Central Institute of Fisheries Technology, Cochin, Kerala. And the esteemed guest has chosen a topic for deliberation, that is non-thermal techniques, scope, and future perspectives. Ma'am, you are audible as well as visible, and your presentation is also visible. You may start.
Okay, thank you. Am I audible now?
Yeah, you are audible as well as visible.
Okay, good morning, everybody. Today I'll be talking about the non-thermal techniques for fish preservation and its scope and future perspectives. As all of us know, fish is very important in the human diet because of its many nutritional properties. It's a good source of omega-3 polyunsaturated fatty acids like EPA and DHA. It's a good source of easily digestible protein, essential minerals like iodine, selenium, zinc, iron, calcium, phosphorus, and potassium. Also vitamins A, D, and several other B vitamins. But at the same time, as all of us know, fish is a highly perishable food commodity. So it requires proper handling, processing, packaging, and distribution if it has to be utilized in a cost-effective and efficient way. And there are many common methods or the traditional methods of preservation for prevention or the control of its spoilage. Like lowering the temperature of the fish as we do in icing and freezing, and like drying, salting, and smoking. Also, we can shift the pH of the environment for preserving the fish, like in pickles and marinades. And there are other heat processing or thermal processing methods like canning and pasteurization for fish preservation. So there are many methods for preservation, but all these methods are energy intensive. So alternative techniques which requires less energy and also have a very minimum environmental impact should be considered. That's how non-thermal fish processing methods have come into the picture. So these are non-thermal processing means processing your foods without the direct application of heat. So the methods where the food material receive microbiological inactivation without the direct application of heat is known as non-thermal food processing. So they are relatively very young technologies, new technologies which use mechanisms other than conventional heating for reducing or eliminating microorganisms. So it offers a substitute to conventional thermal processing. But as I said earlier, why we have to go for non-thermal technologies when there are thermal processing and other fish processing methods are existing? So the answer is the green trend, the inevitable green trend, and also the undesirable changes in the food caused by conventional thermal processing. So conventional thermal processing or the canning, it can lead to loss of nutritional components which are temperature sensitive, and also there will be change in the texture of the food because of heat, and also there will be change in the sensory characteristics of food. And the second reason, as I said earlier, the consumer demand for clean and safe food without compromising the nutritional and sensory qualities of food. So these two are the key drivers towards innovation of the non-destructive, non-thermal food technologies. These are also known as minimal processing techniques. So there will be sustainability in fish processing if we adopt these non-thermal processing methods, because they have a very low energy consumption, and also they reduce the impact on the environment and the quality of the fish. And there are different non-thermal processing methods, and the Pivaronic and Borobo have classified them into processing using pressure, light, ionizing radiation, and gases. So the first one is high pressure processing. This is a non-thermal processing technique using high pressure. Second is processing by light, like ultraviolet and pulse light preservation. Then preservation by ionizing radiation, like gamma irradiation and electron beam irradiation. And the fourth one is processing by gases like ozone, chlorine dioxide, and coal plasma. So the first and the most popular technique is the high pressure processing. This is also known as high hydrostatic pressure processing or ultra high pressure processing. It's a non-thermal cold pasteurization technique. So in high pressure processing, we subject the food which is already subjected to a high pressure of up to 600 megapascal for a few seconds to a few minutes. So it is the same effect as subjecting the food to an ocean depth of 60 kilometers. And this is the diagram of operation of a high pressure processing unit. It has got a pressure compartment. The food will be kept in the compartment. Then water will be introduced into the chamber. Then food is pressurized using this water. So high pressure processing use the very common medium water for applying pressure on the product to be treated. It can cause a decimal decrease in the population of gram-negative and gram-positive pathogenic bacteria as well as yeast and mold. So this will help in food preservation for a long duration. And the reduction of the microbial load will depend on the pressure and temperature during treatment as well as on the type of food processed by high pressure. And let's see, how does pressure inactivate bacteria? The high pressure will affect the cellular functions like DNA replication, transcription, translation, even at low pressures like less than or equal to 100 megapascal. So this will obviously impair the bacterial growth. And when the pressure goes to higher level, the microorganisms will start suffering lethal injuries because of the loss of cell membrane integrity and protein functionality. And the most sensitive microorganisms to pressures are molds, yeast, and parasites. The bacteria, the common bacteria, it requires high pressures in the range of 300 to 600 megapascal for inactivation. And the most barosensitive are bacterial spores. They can survive pressures up to 1200 megapascal at room temperature. Coming to the effect on the product or the food quality. So when the food is subjected to high pressure treatment, it undergoes high pressure. It will be under high pressure for a very short duration of time. And the pressure is, normally the pressure applied is in the range of 200 to 700 megapascal. And the quality in terms of the nutritional component, sensory and texture of the food is excellent compared to other techniques because the food is exposed to the treatment conditions for a very short period of time. So the food will show fresh-like attributes. And these are HPP machines, vertical and horizontal machines, and the trend is mostly towards the horizontal machines. And these are some of the high pressure processed commercial products like juice, meat, seafood, ready meals, sauce and spreads available in the market. And when we talk about the major applications in seafood, high pressure is mostly used for cold post-packaging pasteurization. And the low pressure process is also applied for mollusk shucking, like the muscle which is responsible for closing the shell of the mollusk. They will not be able to contract and the oyster will open. So this will expose the meat for easy extraction and this will result in a significant yield increase. And another, as in the case of mollusk, in the case of crustacean also, we can use high pressure for meat extraction. Crustaceans like lobster or crab, they will contract, the meat will contract and will detach from the shell, and this will facilitate the extraction with yield almost 100%. Then the question comes, can we use the high pressure processing technique for processing of all foods? The answer is no, because high pressure processing cannot be used. It is unsuitable for solid foods with air included like breads and cakes, mousse, and also package the food in completely rigid packaging like glass packaging, canned foods, and also foods with a very low water content like spices, dry fruits, powders, etc. So the food with entrapped air or the solid food with air included and also the food with insufficient moisture content, they will be crushed or compacted under high pressure. So high pressure processing cannot be used for solid foods with air included and also food packed in rigid packaging and also food with low water content. And these are some of the studies conducted at ICAR-CIFT using high pressure processing machine. Jinsen et al. Studied the effect of high pressure treatment on microbiological quality of Indian white prawn during chill storage. Then Kundat et al. Reported a synergistic effect of hydration and microbial transglutaminase on the textural and functional properties of fish gills compared to conventional cooking. And Devatkal et al. Used high pressure processing as a technique to improve the shelf life and quality of cooked refrigerated chicken nuggets. And Kundukulangara Pulisheri et al. Compared the textural and nutritional profile of high pressure and minimally processed pineapple. And Jinsen et al. Investigated the piezo tolerance and diversity indices of microflora of Indian white prawn at high pressure after high pressure treatment. The second non-thermal preservation technique is pulse electric field processing. This is also a very efficient non-thermal technique using very short high voltage pulses. So this can be used for inactivation of spoilage and pathogenic bacteria in various food products. And the inactivation of microbes is achieved by dielectric breakdown of the bacterial membrane. So the food material will be placed between electrodes, typically between 20 to 80 kilowatt per centimeter, and the pulse frequency time varies from 10 to 10,000 microsecond. So this is a mild preservation technique. This applies electric pulses to destroy the bacteria in the food and can prolong the shelf life of the food without affecting its quality. And the mechanism is electroporation. Very short electric pulses of high voltage will be applied to the food, and there will be small pore formation in the cell membrane of the food by electric pulses without damaging other cell components. Of a typical PEF device, it has got a food treatment chamber, a control system, and a pulse generator. The food is kept in the treatment chamber in between two electrodes, and but this technique is generally used for liquid food or semi-solid food that can flow easily. That's a demerit. And coming to the applications of PEF in fisheries, this can improve the water holding properties of fish. This can be used for tenderization of shellfish. Then also the efficiency of the extraction procedure can be improved using pulse electric field technology, especially to obtain protein from mussels. There are reports about it, and it can also be used as a pre-treatment for drying. And also this has been used by various researchers to valorize byproducts from fish processing industries. And also it has been used as a method to extract calcium from fish bone, and also for extraction of chondroitin sulfate, extraction for isolation of the abalone viscera protein, and also has been used as a pre-treatment of fish waste for enhancing its yield. Coming to the advantages of pulse electric field processing, it can maintain the properties or the physical, organoleptic and functional properties of the final product can be maintained if we use pulse electric field processing, because it will cause very minimal changes in the flavor, vitamins and other nutrients in the food in a very homogeneous way and very rapidly. And this can reduce the process time, and the energy consumption is very low. There is a continuity in the process. This is a very efficient and eco-friendly technique. This can enhance the shelf life of the food, and this is more effective when we use it with other methods. And when we talk about the limitations, the main barrier or the main limitation is the high initial capital investment. So this limits the application of this in the fish processing industry at present. Of naturally occurring enzymes in the fish. So this is another shortcoming. And the electrical conductivity of the food product, which is a very crucial parameter. So this also limits the application of this particular preservation techniques to only materials with moderate conductivity. And coming to the third technique, that is irradiation. Irradiation is nothing but this is a process where an object is exposed to radiation. This is a deliberate exposure to radiation. And there are two forms of radiation. You all may be knowing that there are ionizing and non-ionizing radiation. Ionizing radiation includes high energy electron beam, X-rays and gamma rays, which are characterized by high frequency and a powerful electromagnetic radiation. And the IR will lead to production of charged particles or ions when it comes into contact with the material. So it will lead to production of ions. That's why they are called as ionizing radiation. And non-ionizing radiation includes ultraviolet rays, UVA, UVB and UVC. Also visible light and infrared radiation. But they generate heat, but they don't generate ions generally. In the case of food radiation, the food is treated using ionizing radiation. So low levels of ionizing radiation will be applied to food materials to sterilize the food or enhance its shelf life. What radiation will be doing is it will break the chemical bonds and it will kill microorganisms, insects, and it will also inhibit ripening in fruits without generating heat. And there are two approaches to irradiation. One is using radioactive isotopes like cesium or cobalt. And the second technique is we can use electrically generated radiation like X-rays or electron beams. When we use isotopes, they produce penetrating gamma rays. So you require expensive facilities with heavy shielding because the radiation is always on and it can pose a hazard to the workers in the system. But when we use electrically generated radiation like X-rays or electron beams, they have very less penetration strength. So this is useful only for surface sterilization, or you can use it only on thin products. But this is much safer and less expensive to use because this can be turned on and off as needed. So it does not require any heavy shielding as in the case of isotopes. And these are the dose ranges for food irradiation application. Means for different food products, the dose level varies. Means even with the applications also, the dose varies. In the case of low dose level, which is less than 1 kilogram, this is usually used for inhibition of sprouting of vegetables like potato, onion, and other tubers, and also for insect disinfestation in stored grains, pulses, dry fruits, etc. And then also for use, also for destruction of parasites in meat and meat products. Coming to medium dose level, which is between 1 to 10 kilogram. This is used for shelf life extension of meat, poultry, and seafood by eliminating vegetative bacteria, which is responsible for spoilage of food, and also for elimination of other pathogenic organisms in meat, seafood, and poultry. And also this can be used as a treatment for quarantine purpose of fruits and vegetables. The high dose, which is more than 10 kilogram, is used for hygienization of spices, vegetable seasonings, and also for sterilization of food for special requirements, and also for shelf-stable foods without refrigeration. So these are some of the foods which are commonly processed by ionizing radiations. The works which are reported are on potato, onion, spices, dry vegetable seasoning, fruits and vegetables, ground beef, pork, poultry, and seafood. And coming to the labeling requirements, the irradiated foods need to have either treated with radiation or treated by irradiation label. It has to be displayed prominently on the food. The symbol is the Radura. You can see the green symbol, Radura. This is a radiation symbol. It must be displayed. Coming to the merits of irradiation, the merits are like this process has minimum effect on the quality, taste, appearance, and texture of food. And it can meet the demand of the consumers for minimally processed and safe food. And this can not only destroy microbial entities, this can also inhibit insects, mites, and pests. And this is an alternate technique to detoxify aflatoxin present in the food. That's very important. And the processing time is considerably less. This is an eco-friendly technique, and this doesn't leave any chemicals or residues in the food, which is treated by radiation. So these are some of the merits. And this is a study by ICAR-Central. Anomaly et al. Has assessed the effect of electron beam irradiation on the biochemical, microbiological, and sensory quality of vacuum-packed headless Vanami during chill storage. And she could get a significant reduction in Brocotheris thermosfacta and lactobacillus count in the irradiated sample. So, and the product had a shelf life, the control had a shelf life up to 12 days, and the irradiated sample had an extended shelf life of 15 to 23 days with respect to dose level. And the fourth technique is ultrasound processing. Ultrasound, as we all know, it's a sound wave bearing a certain frequency that is more than the normal human hearing frequency. That is about 20 kilohertz. So when the ultrasonic waves oscillate through the medium, they will generate many expansion and compression effects in the medium. So there will be formation of small cavities due to the presence of air. So the cavities will grow to a desired size and then it will collapse. So when these cavities collapse, they will generate a large amount of energy and local hotspots. So there will be an increase in the heat and mass transfer rates consequently. And the ultrasonic waves, the energy generated by sound bubbles in liquid media, which will produce a high temperature and pressure increase when they immediately burst. So the bursting of the bubbles also emit light. It's a form of energy transferred from the sound wave, so it's called as sonoluminescence. And the ultrasonication can be classified into low frequency, medium frequency, and high frequency ultrasonication. A low frequency varies between 20 to 100 kilohertz, and medium frequency varies between 100 kilohertz to 1 megahertz, and high frequency 1 megahertz to 100 megahertz. There are two different methods of application of ultrasound. The first is using an ultrasonic horn. The horn will be dipped into the liquid solution or the juice, which is treated with a certain treatment frequency. Then the second method is using an ultrasonic bath. The food material or the packed food is kept and the sound waves are generated in a bath that creates ultrasound effect. This will bring about the desired changes in the food. So the mechanism is mainly the microbial killing is mainly due to thinning of cell membranes, localized heating, and production of free radicals. And these are some of the application in the food industry. So ultrasound can be used in freezing applications. This can improve freezing by better preservation of the microstructure of the food. And the freezing assisted by ultrasound requires less time and small crystal size. This can improve diffusion, and also there will be a rapid decrease in temperature. And this can also be used for thawing. So ultrasound will reduce the thawing time. This will preserve the color of the food. This will inhibit lipid oxidation. Product quality will be enhanced, and also the dehydration in the product will be reduced. Ultrasound can also be used for brining or pickling, and also for drying. And there are other applications like filtration, formation, extraction, sterilization, rehydration. So ultrasound can be used as an additional preservation method. This can be used along with other methods to improve the efficiency of other methods. The merits of ultrasound processing are, as in the case of many other non-thermal preservation techniques, this is also an eco-friendly or a green technology. So this, in the food industry, and intensified synthesis, and the physicochemical and properties of the food will be improved. So we can expect production of a better quality product at low temperature with an improved rate of heat and mass transfer. Coming to the demerits, there is a very limited technical information about ultrasonication. That is one of the limitations of this technique. And when we use ultrasound, when we apply at high intensities, this will generate heat because of the escalation in temperature. So this will have bad effects on the organoleptic and nutritional character of the food product. And consumer awareness about ultrasonic processed food is also another limitation. Very limited awareness is there. And the next technique is preservation by ultraviolet radiation. So this is a very economical non-thermal technology. This can be used for decontamination of the foodstuff, and also this will reduce the microbial load on the surface of the food materials which are indirectly exposed to radiation. So, and UV can be classified in the UVA, UVB, UVC, and UV vacuum. And the UV in the wavelength range of 200 to 280 nanometer, which is usually known as UVC. This only has, in general, this only has germicidal property. So when food is exposed to these short wavelengths are absorbed by the microbial cell nucleic acids, and this will lead to breakage of the bond and interlinking between thymine and pyrimidine of different strands, and subsequently there will be formation of dimers of pyrimidine. So these dimers will prevent DNA transcription and translation, and also it will lead to the malfunctioning of the genetic material, and ultimately it will cause microbial cell death. So in principle, the UV radiation operates by destroying the genetic constituents of the pathogen to prevent division, multiplication, and subsequently it hinders its propagation. So usually different kinds of food products require different doses of UV radiation to inactivate different kinds of pathogens. For bacteria, the UV inactivation dose is 1 to 10 mg per centimeter square, and for yeast is 2 to 8. And the most resistance, the one which is require highest dose is algae. The dose range is 300 to 400 mg per centimeter square. And there are some factors which affects the efficiency of the UV radiation. These factors are, one is the source and dose of the UV radiation, then the duration by which the product is exposed, then the nature of the food, then alignment of the apparatus, and as well as the nature of the microbe. The merits of these techniques are the lethality effect of the UV radiation, which is very high compared to conventional chemical agents like hydrogen peroxide and chlorine. And also it is very easy to use, and it is a cost efficient technique, and it has very minimal effect on the quality of the food, and it also prevents recontamination because it can be applied in already packed food products. It is environment friendly. This can not use not only for liquid products but also for solid food products. We can use a UV radiation technique. The processing time is very short. This also shows outstanding permeation capability to food. Our next technique is pulse light preservation. This is an alternative to continuous UV treatment for solid and liquid food. This consists of successive repetition of high power pulses of light or short time high peak pulses of broad spectrum white light. So the light spectrum include wavelengths from 180 to 1100 nanometer with a considerable amount of light in the short wave UV spectrum. And the intensity is 20,000 times that of sunlight at sea level. And the pulse xenon UV, this uses the full spectrum of ultraviolet light to disperse germ killing energy. This is a pulse light equipment which we have in ICAR-CIFT at Cochin. So this has got a sterilization unit. The sample is placed below the xenon lamp inside this chamber for treatment. Then there is a blower. So this will purify the air inside the sterilization unit, and there will be a cooling effect for the lamp. This will increase the life of the xenon lamp. Then thirdly, there is a pulse generator. The electrical energy is converted into short duration pulses of broad spectrum white light by pulse generator. Merits of this technique is this can act as a rapid disinfectation food processing technology. This causes very less damage to the nutritional property of the food, and this has, the technology has a, when we compare it with UV radiation, because it exhibits an outstandingly short time energy transmission. So there will be a substantial reduction of bacteria in an exceptionally short time. It has huge adaptability. It is an eco-friendly technique. It can be applied for prevention of contamination of packaged food products. And the next technique is cold plasma technology. Plasma is nothing but the fourth state of matter after solid, liquid, and gas. Solid is converted into liquid, liquid is converted into gas, and when again the energy of gases crosses a certain value, it results in the ionization of gas molecules. So the ionization of gas molecules will produce plasma. And there are two types of plasma, thermal plasma and non-thermal plasma. Non-thermal plasma is also known as cold plasma. So cold plasma, it's a non-thermal treatment because it works in the temperature. So when the gas is ionized, free radicals like ions, electrons, etc. will be generated, and the composition of the plasma will depend on the composition of the gas which is ionized. So the gases which are commonly used for generation of plasma include argon, helium, oxygen, nitrogen, and air. And coming to cold plasma generation, the gases are subjected to any of the type of energy like thermal, electrical, magnetic field, etc. to generate plasma containing ions, positive ions, negative ions, and reactive species like ozone and singlet oxide. So the methods usually adapted are radio frequency plasma generation, dielectric barrier discharges, then gliding arc discharge, microwave, and corona discharges. These are the common methods for cold plasma generation. And coming to the advantages and application, cold plasma can be used for reduction of microbial load in the food or on the surface of food. And this can enhance the physical and chemical properties of food, and also there will be less damage on the constituents of the food like lipids and proteins. And this can help in sterilization of food processing equipments. The food spoilage enzymes can be inactivated by cold plasma. Food packaging material can be treated by food plasma, and also this can be used for treatment of wastewater. And another important thing is cold plasma is generated at near ambient temperature. So it does not depend on high temperature for micro. is ambient, there are no chances of thermal damage to heat sensitive food material. Another technique is ozone treatment. Ozone is it's a colorless gas with a typical odor. It contains 3 molecules of oxygen. So when a molecular oxygen combines with a singlet oxygen, ozone is formed, and it's a very reactive gas. It's very much unstable, so it cannot be stored. So it has to be produced on the spot when needed. But it's a grass chemical. It is generally recognized as safe, but with the USFDA approval. So it is used as an antimicrobial additive for a direct contact with food. Ozone is already widely used as an effective antibacterial against many bacteria in the food. This can be used in gas form, or it can be mixed with water to form ozonated water. So this can be used in 2 different ways. This is a chemical method of food decontamination. This involves exposing contaminated foodstuffs like fruits, vegetables, beverages, spice, fish, meat, etc. to ozone. The food will be exposed to ozone in aqueous or in gaseous phase. Ozone will alter the permeability of the cells by damaging the microbial cell membrane. That's what ozone do to microbes. Ozone is also known to damage the structure of proteins. This will lead to malfunctioning of microbial enzymes. This will also affect the metabolic activity. And finally, it will result in microbial cell death. So ozone will alter the permeability of the cells and also damage the structure of proteins. There are other techniques also. I have discussed only the major non-thermal food preservation techniques. Then there are many other techniques like supercritical fluid extraction and many other techniques are there. I have not discussed some of the techniques. I have discussed only the most important non-thermal preservation techniques here today. And about the future prospects of these techniques, I think it's very important for the food or the seafood industry to fully understand the mechanism of action as well as the merits and demerits of each of these techniques before they implement these techniques in their system or in their factory. And also the mechanism, the process mechanism of each technique should be streamlined. And also there will be a consumer education. The consumer should be educated about the strength and prospects of these non-thermal technologies to raise more awareness before they consider it. And also there should be a deep evaluation of the processing line by HACCP methodology. Techniques, and also developing a hurdle like non-thermal technology will be more beneficial. And also it is very important to know the prerequisites by the manufacturers. We should be adhered to these prerequisites despite the variation in the facilities or equipment or operational or production scales, etc. So we should be, it is very important, the prerequisites. Thank you all.
Thank you, ma'am. Now, if there are few questions, we can, we have few minutes left. If we have any interaction or question we would want to ask, then we can consider the session over after the questions and interaction is over. Participants can turn on their microphone. If they have any questions, they can ask. Any questions or interaction? Ma'am, I don't see any questions. And on behalf of the participants and on behalf of the organizing committee, we extend our heartfelt gratitude to you for being with us, for sharing this lovely presentation, ma'am. This was so nice of you, and we look forward to collaborations for future programs with you. Thank you, ma'am. Thanks for being with us.
Thank you very much. Thank you
Thank
for
you,
the
everyone.
opportunity.
Thank you, everyone.